Okay, welcome everyone. We are already at Tropical Geometry Part 19, or how I like to call it, Tropical Linear Algebra 3. Right? Tropical Linear Algebra, this idea of doing linear algebra in the tropicals, and everything you do actually is some form of accounting problem. That's what tropical geometry or tropical arithmetic actually does. And today I would like to talk about or tell you about taking the powers of a matrix. Right, so usually I will recall the classical story, something like a cubed is equal to whatever, and we usually want the power to be large, whatever. So maybe like more like a to the 300 is equal to whatever, and we'll see what is actually encoded in this expression. Right, that's the whole point. So classically, I would like to do the following. Again, this is one of the. It probably has appeared like 1,000,005 times now on this channel because I like it so much. The most underrated fact of linear algebra: matrices and graphs are exactly the same object. How is that, you might ask? Well, you just draw your graph, whatever, and you draw a matrix of size vertices times vertices. So here 4 vertices, so a 4 by 4 matrix. And every entry corresponds to, is there an edge from I to j? So there's an edge from 3 to 2. So is there an edge from 3 to 2? From 3 to 2, right? Here 3, here's 2, there is an edge, and we just record the label, right? Is there an edge from whatever, 3 to 1? Yeah, there is an edge of label 8, like something like that, right? So and then you can just go and record your matrix. And vice versa, if you have a matrix, you can just record the graph. It's really the same type of information. So matrices and graphs are essentially the same object, right? Highly underrated fact of life, if you want. And what you usually do here is if there's no edge, then we call that connection 0, right? So there's no edge from 4 to 2. So there's no edge from 4 to 2, so we put in a 0 here, for example, right? Matrices and graphs are really the same object, and everything you can do for matrices, you can do for graphs. So, for example, for matrices, eigenvalues are very important. For graphs, eigenvalues are very important, and so on and so on and so on. Counting things in matrices correspond to counting things in graphs. The particularly strong connection is for integer matrices, because then my number here really just would represent, like, let's say 4 parallel arrows, right? Something like 1, 2, 3, 4. While if it's just a random real number, pi is not a random number, but a real number, like pi, I really would just label the edge with a pi. And it doesn't have any particular meaning, except you can think of it as like the cost, right? So think of this as like a network, and every label corresponds to the length of what you want of the edge. So something real world, and to go from city 3 to city 2, you need 4 units of time, for example. Or whatever your units are. So this is the relationship between matrices and graphs. So then what is the relationship between matrix powers and graphs? Well, okay, here's our matrix again. And these are really just the connections, right? So here's our edge from 3 to 2. I put a 4 there. So the cost going from 3 to 2 is 4, right? There are 4 edges from 3 to 2. There are 4 edges from 3 to 2. In the second power, there are now 48 edges from 3 to 2. That is a lot. And why are there so many? Well, this entry in the first power measures the number of paths of length 1, first power, length 1, from whatever I to j, 3 to 2. And this would be in the second power, the number of paths of length 2 from I to j. So how many ways are there to go from 3 to 2? There are quite a few. I could go 2 and then 4. So I have 2 options times 4 options, seems to be 8 options. Or I could go 8 and 5, right? 8 options here, 5 options here, seems to be 40 options. So in total I should have 48 options, and indeed. So the second power measures the number of paths of length 2 from any vertex to whatever any other vertex in the ij entry. The third power would measure the number of paths of length 3. So maybe I'm not going to discuss this entry again. It looks very, very large to me. Let's try this one. So apparently there are 4 ways to go from vertex 2 to itself in 3 steps. Okay, so 4 ways. So we could do, in 3 steps, we can't use this loop because we end up in 1. In 3 steps, we can only do that, as far as I can tell. And indeed, there are 4 ways, right? 1, 1, 4. So the number of paths of length 3 is 4. Observation, It's not difficult to prove, but right now let's call it an observation or fact. The entries of m to the k correspond to the number of paths of length k. So what happens tropically? It's kind of a nice fact here about matrices and graphs, and you might wonder, what happens actually tropically, right? What is the log of that thing? First of all, if you take a log of that thing, instead of putting 0, you put infinity. And you see in a second why I want the diagonal to be 0, right? So you just put zeros on the diagonal, and whenever there's no edge, you put in infinity, and otherwise you keep your matrix, right? So there's no edge from 4 to 1, so there's no edge from 4 to 1, so I put it infinity here. And then I take the tropical powers, here the second tropical power, and I get a new thing. Just keep in mind we have this plus and min type operations. And this now, it's kind of interesting. It's not the number of paths, but it's now the cost of the shortest path. Yeah? So m to the k, the cost of the shortest path. And how this behaves is, oops, I shouldn't have done that, is that here, careful here, it's really the number of paths of length k in the k step. You don't count the paths that are shorter, just the ones of length k. And here you also count the things that are shorter. That's why you want to have the 0 on the diagonal, because the cost to going from I to itself in the shortest way is, of course, you don't do anything, right? You just stay where you are. And otherwise, something like to go from 1 to 2 is cost 5, and of course it is cost 5. To go from 1 to 4 should be cost something like 6. From 1 to 4 is cost 6, right? Note here, from 1 to 2 was already cost 5 to begin with, and it stays the same, right? So we are measuring the cost of the shortest path. And of course, if I just want to go from 1 to 2 in 2 steps, I could just stay there after 1 step. Okay, hope that makes sense. So this is really measuring travel cost. Classical matrix powers number of paths, number of options, and here travel cost. Right? Hope that makes some sense. So tropical matrix powers measure the travel cost, right? So then just formulated, a tropical adjacency matrix satisfies the ij entry of m to the k is the value of the cheapest path from I to j of length lower or equal to k, right? Lower or equal to k, right? And this is really what it is. And kind of funnily, this implies that from a certain power onward, this really just stabilizes, and you can already see that here, right? So this entry is really just the same as before, and it will not change. The shortest path from 1 to 2 is always 5. So you can take 15,000 more powers here, and it will not get any cheaper. So these kind of matrices behave very interestingly, while the classical ones will just grow all the time, because you count the number of paths, there will be more and more and more and more. Here it really just stabilizes after a certain number of steps. A very, very non-classical behavior, which people usually call kind of this idempotent type behavior. It's really way more like a monoid type object. So an idempotent is this idea that e squared equals e, right? So it's kind of a minimal type of, so when k is 1 something, yeah? So kind of a minimal type of operation here, a minimal type of property that appears here. And if you don't know what an idempotent is, usually those buttons here at streetlights, they're idempotents, which really means, let me say that in words, if you press it once or you press it twice, it's the same. If you press it once or you press it 500 million times, it's the same. So please leave the button alone, just press it once. Yeah? You don't need to press a million times. It's an idempotent. It won't change anything. Anyway, and tropical matrices behave in the very same way. So you can easily think about an application. So here is, you probably can't see anything. It's like the flight maps of the world or something. And you want to have the task to find the price of the cheapest flight from A to B. I don't know, maybe we want to go from Sydney to whatever that spot there is, and maybe you want to go like that or something. And you just write it down in your matrix, take a certain power, eventually it will stabilize, and then you just look up the number you find. That's the cheapest price in this case from A to B. And you can, of course, come up with plenty of other applications along the same lines, right? Anyway, I hope you enjoyed this video, and I hope to see you next time.